He knew for real.
I agree. All right.
Last year, how many classes did you see last year? 10?
8.
How? That's more than 10.
I had 2 virtuals on top of my 6 regular classes. I tried to explain to them that that was 8 classes, and they're like, "No, it's 6 because they're on top of your regulars." I'm like,
That's still on top
"Is that out of your mind?" Like it was like I was talking to a wall. I went, "I still have to make up virtual tests. I still have to deal with these people because it's hard for them to communicate, and they're not. I still have to contact them. I still have to do all that. How do you figure?" No, you don't understand. They're on top of your other classes. If I punch you, will you hear me better? At some point, somebody was finally honest, and they're like, "Mr. Herb, I'm going to be totally honest with you. Kind of sucks for everybody." So they listed off a bunch of other ways other people were getting screwed over, and they are. Like there's like one person had 5 classes. Like I get paid for 6. Most people, their stipend is 5. I mean, their salaries for 5. One person had 5 classes and 150 kids. I had 6 classes and 120. So they had virtual classes with like 40 people in them.
Oh, yeah.
Well,
Miss Dark had like 6.
Yeah, Miss Dark was getting screwed. And they finally fixed that and paid her for a 6th class. But it wasn't after people like me and Gossett and whatever went to battle. And it's like, what are y'all doing? Like I know I'm getting screwed, but they're really getting screwed. So they finally did, I think, pay her. But I think it was just so unusual a situation. I don't think their intent was to screw over anybody. They were just trying to figure it out. So I understand sometimes things just stink, but that doesn't make it feel any better. And that's another thing. It was like a brand new world everybody was living in. So it's like there's so many different things, working parts that everybody's trying to juggle. I think ultimately they were trying to make a situation great for students. And they're like, hey, we're not going to just, like a lot of schools just went, throw them all to a virtual platform. There are people out there that teach virtual classes. But Homewood was like, you know what? We want to be better than that. We want our teachers teaching our kids. So they tried to do that. They just had no idea the impact it was having on the teachers. Like teachers were just like emotionally falling apart. I mean, I had a horrible first semester. I faked it all semester. Finally got some good counseling from a friend. But anyway, that was just, I just don't think they realized in trying to be great to kids what they were doing to their teachers. You know, so that's why this year they're like, if you want to go virtual, knock yourself out, but you will not be with a Homewood teacher. I mean, you're not going to learn that. It's like there were 5, I don't know if I said this, but there were 5 virtual calculus kids that I did not teach those. There were 5. Their scores on the AP test of those 5 kids that were virtual were 1, 1, 1, 2, and 4. We averaged, does that even spell average? We averaged a 4 on our kids. And the national average was a 2.8. I mean, to put that in perspective. So our kids averaged a 4. That's what they got virtually. So that's what you get in a virtual platform. It's not Homewood teachers typically. It's just terrible. And consider that a lot of that's probably, I mean, a lot of what you're getting is kind of I mean, you be honest. When you sent you home in that spring quarter, that first year of COVID, did anybody, well, you don't have to be honest. Most people were open notes, whether it was open notes or not. A lot of people were sitting next to their buddy while they're taking their test. I mean, people just didn't learn like they should have learned. I mean, we tried to push something out, make it something, but it's ultimately it was just, hey, it was what it was, right? I mean, nobody had a plan for that. What do? You just make the best of it. So
yeah, that didn't work out.
It almost caught. I mean, I almost didn't come back. So thanks.
My education thanks you. I also thank you.
Yeah, you're welcome. All right, what are we on? Implicit differentiation, AP.
Sir, what would you do if you didn't come back? What would you do?
Honestly, and this may happen next year, I would probably come back on a limited basis, like maybe teach a couple classes in the morning. Like literally my salary wouldn't change, which is ironic because my retirement would kick in. So literally I'd be working 2-3 hours a day and making the same money. So I could do anything at that point. I'd have 11 to on free. And who knows, I could buy a house, fix it up. I mean, I'm very handy. I'm a good little carpenter. I mean, I can fix stuff and that interests me. It's something different. My mind's flickering everywhere all the time. So doing something different all the time is awesome to me. Doing the same. That's why I think even though I've taught the same subjects for so long, it doesn't feel different because there's different faces and different brains interacting with me. So it feels different. But anyway. All right. I don't have this labeled very well, do I? I'm looking for trough problems.
Oh, I think it's front and this on. 57.
57. Oh, okay. I'm way down the list. Okay. So, we've done the ladder, blah, blah, blah. All right, here we go. Trough problem. All right, this is shown up on an AP test a number of different times. We're 57 in your notes. And you see it different ways. But bottom line, there's this trough and water is pouring into this thing, right? And as it pours in, it fills up, right? Now you can imagine as my water level rises, it's going to take more water to make it rise from, say, the 7 to 8 than it is from the 1 to 2 because there's more volume to fill, right? So you can see that the height right here and the width right here and the volume, those are all going to be different rates. And it might fill up quicker at the beginning. It might start rising quicker at the beginning and then slow down because there's more volume, whatever, because it's coming in at a certain rate. And right here, that's a different question. Okay. So the first thing I'm going to do if I'm going through this process is to think, okay, clearly what's being affected here is the volume of water in this trough. So let's see if we can come up with a volume equation. All right. So remember what we said about volumes. If the cross section never changes, then I can use the volume of that, the area of the cross section times the length. Just like a cylinder, if the cross section never changes, I can use the area times the height. All right. So right here, obviously the cross section here changes, right? It's always a rectangle, but it's changing. But the cross section here doesn't, does it? So I need to find the area of this triangle times the length. All right. Or a formula that will help me with that. So how would you find this right here if I'm dealing with a volume of this thing? I want to have what? Base times height times length, right? So base times height would give me the area of that. I'm sorry, 1/2 base times height because it is a triangle, right? So 1/2. And I know base, we typically think base on the bottom, but this triangle's pointed downward. So base, whatever that is, height, whatever that is, length, whatever that is. So 1/2 base times height times length. All right. Now, of the base, height, and length, as water fills up, are any of them not changing? The length. So the length isn't going to have a rate at which it changes. It's always 12. Can y'all see that? But as the water rises, you can see the height's getting bigger. That base value is getting bigger, but the length is always the length, isn't it? So we said if there's ever a side like the ladder, remember the ladder? It was the side of the triangle, but it never changed. Then I want to put that number in. But I do not want to put a number like right here. If you go back to this, if you go back to, and that eraser is the gift that just keeps giving right there, isn't it, man? So if you look at this right here, this right here is changing, but that length of 12 is always 12. So I'm going to come in here and I'm going to replace length with 12, and that reduces this equation to 6 times base times. You know what? I'm going to quit using B and H. Base and height. I'm going to just use B and H. So I have 6. That's a 6 right here times base times height. Okay. Now, at this point, I'm ready to implicitly differentiate, but I'm going to wait a second until I write down all of my information. So my information here said water is being pumped in at 2 cubic feet per minute. So what is that giving me? The rate at which volume is changing, right? So that is a what? dVdt. So I have a dVdt, and it told me that that rate was 2 cubic feet per minute. Is that positive or negative? Positive, because it's getting bigger in that trough, right? So that's a positive 2. It says, how fast is the water level rising? What is that saying? Is it just, it didn't say what is the height of the water level. It says, how fast is it? So what is the rate at which the H is changing, dH dt? So how fast is the height changing when what? So when what? When H is 1. So I'm looking for that particular height when H is 1.
Is that negative?
Well, that's going to end up, well, no, the H is the length, right? But that's going to end up being positive 2 because that water level, that height is changing. It's getting bigger and bigger, right? So this is the information I have. So I'm looking for, I have a dVdt. I'm looking for a dH dt. So when I look back at this equation, I'm like, well, I'm fine on the V being there because the dVdt is going to show up. I'm fine on the H being there because the dH dt is going to show up. But I am not fine on the B being there because the dB dt would show up, and I don't know anything about the rate at which the base is changing. And I really don't want to do another related rates problem with that. So what I got to do now is go, well, is there a relationship that I see here between the base and the height? Well, if I look at this triangle, what do I see? The length of the base and the length of the height are equal. Now, if they're equal, then B and H are the same thing, aren't they? And I could say B equals H. But let me caution you. A lot of times they're not equal. So what I do is this. I just go, all right, I set up a proportion. As my height gets bigger, my base changes, typically speaking, right? So I'm going to say, all right, base over height equals, and I write down the base value, and I write down the height value. And then I just solve for whatever variable I want to get rid of. Does that make sense? So that way, this is going to be off all day. The reason why I write it like this, even when it's obvious in this situation, you're going to cross multiply and solve and you're going to get B equals H. But sometimes you're not. Like sometimes I'll tell you, hey, the base is 2 when the height's 3. Well, if that's the case, I could go B over H equals 2 over 3, and I can solve for B and have that ratio for me. And I don't have to overthink it. Y'all with me? You'll see another one of these where they're different. But in this case, I cross multiply, 3B equals 3H. I want to get rid of that B, so I solve for B and I get H. Now again, I overkilled it there. I didn't need to do that. But this lets me replace the B with an H. So when I replace it, now I have 6H squared. Now I'm ready to go. Because when I take a derivative now, I don't have to worry. What'd I say?
No, it's not you. I'm confused for sure.
Now I don't have to worry about the dVdt being in there. Y'all seeing that? So this is me basically going back to geometry, right? I'm going back to geometry and saying, hey, what do you know about a triangle if that's the B and that's the H? And if I said, well, if the base is 2 when the height is 7, then you could say B over H equals 2 over 7. You set up a proportion. And that way, if I have a smaller one in there, like a smaller rectangle is still going to have that same, a smaller triangle is still going to have those same proportions. All right? So that's what I do. Think like this. Even this one, it's kind of obvious because the base and the height were the same, but it's not always the case. So anyway, now it's pretty easy to take the derivative, right? So the derivative of this is dV dt. And the derivative of this is 12H dH dt. Can't forget the dV dt and the dH dt. And at this point, again, I don't know why I have all this here. But at this point, I just got to plug and show. So do I know dV dt? Yes. Do I know the H value? Yes. Do I know dH dt? No. But that's what I'm solving for. So I divide by 12 and I'm good. So dH dt is 12 over 2. So you have 1/6. And what is height measured in? So height was just feet though, right? Volume was cubic feet. That height was just feet. So think of the unit like if height is a length, area would be a square, volume is a cube, and then time is minutes. So there's my dH dt. And now that I have it, at least at this moment, remember, by the way, if I go back on another question and say, hey, what's the rate of change of the base when the height's 3? You can't go back in the next problem and go, oh, 6BH. Now I know dH dt. So I can use this dH dt in here. Well, remember, this is the dH dt when? At a height of 1. So if the next question came back and said, oh, now I need to know what is the dB dt at a height of 3, I can't use this. I can only use this dH dt if I keep sticking with that height of 1. Are you with me? That's why I think sometimes it's safer not to reuse what you found, because if you reuse what you found and it's wrong, it's going to hurt you. And if it's right, even if it's right, sometimes they change the parameters for you and you could still end up getting hurt. Yep.
Would it be possible to go back to work?
Maybe if we can get done with today's stuff, which is going to be tough because it's a short period. All right. So the next question they asked you, if the water level is rising at that, when the height of the water H is 2, see how they did that? They changed the height to 2. So, but what did they give you? If the water level is rising, so that is the what? The dH dt. It says at what rate, determine the rate at which the water is being pumped into the trough. So basically they're saying, hey, if the water level is constantly rising the same, then the rate must have been changing, right? Because it takes more water to get it to rise constantly towards the end because it's more area, more volume to fill up. Does that make any sense? So they're basically saying, forget what you had before, but what is this giving you? Water is rising at that rate. That's what? dH dt when H is 2. So let's go back up. Let's go back up and say, all right, what if the dH dt, what was it again? 3/8 when H is 2. Okay. So it says determine the rate at which water is being pumped in. So I'm saying, what is dV dt? What is the rate at which the volume is changing? Water is being pumped in. Well, I still have what? Volume equals 1/2 times the base times the height times the length. And again, the length's not changing. So I'm really right back to this equation again. I know I'm looking for dV dt, so that's fine. I know dH dt. That's great. So what do I want? Again, I want to replace base with what it's equal to. And in this nice situation, it was H. So I'm back, in this case, to the same thing. I'm going to dV dt this. I'm still going to get 12H dH dt. But this time what? I'm plugging a 2 in for the height. The rate at the height was changing was 3/8. So my dV dt is what I'm looking for. And I can cancel some of this. So 9 what? Volume would be measured in feet what? Volume is feet cubed. So feet cubed. Y'all know that, right? Volume is always a units cubed. Area is a unit squared. Right? Length would be just a unit. And then time again, minute. So you can see literally the volume, the first problem, the rate was fixed. So if I'm fixing it like a hose, it's the same coming out. You're going to see it start rising, but then as it get higher and higher, it slows down the rise. But this is saying if the rise is constant, which would be constant in a cylinder, you got a cylinder, right? And you have a constant volume, you're going to get a constant rise. But if you have like a cone or a V, the only way to get a constant rise is to keep increasing the volume rate. You'd have to pump more water in as you moved on to be able to keep the rate climbing. And you can see the rate of change of which the volume is 9 feet cubed. So like every minute, it's 9 more whatever feet cubed, whatever that is. You get 9 more of those per minute. So anyway, I don't know a situation that's real, but whatever. All right, what about I don't know why I don't rewrite this problem. I was like Penn and Teller cylinder problem. Whatever. We're gonna go with it. I don't know if this is an old AP problem. This is old as dirt. Some of these problems. AP used to give they used to give a lot of these as 9-point free response questions. Like there were 9 points. There's 6 9-point free response questions, and most of the questions have subparts, like a part A, a part B, a part C, a part D, and or at least ABC. These I haven't been able to find a 9-pointer since maybe the early 80s, late 70s. So most of the problems I have are really, really old. So they show up now as little 1-point multiple choice questions, or maybe recently there was a 3-point part of a problem, or it was a related rates problem, but it's not a big deal on AP like it used to be. It used to be like, you better know related rates. So we probably overdo it and spend more time on it than we probably need to. But it does show up in college a good bit. And it's kind of a real life situation in that you do see rates changing in physics and also in chemistry, things like that. So whatever, I've got a cylinder, right? So through the miracle of illusion, right? So I've got this cylinder. I'm going to go ahead and sketch a cylinder because I find that that's helpful to me. If you stink at art, I understand. All right, so I got this cylinder, and it says the rate of change of the volume is increasing. Now, what would be the volume of a cylinder? This is something that you would have to come up with. Well, remember, so the area of the base times the height. So I don't have anything labeled right now. So if you want to, they didn't give you stuff. So I'm going to call that radius. So the area of the base would be what? Pi r squared, and you could call this height. So pi r squared h would be my volume. So those are the kinds of things you would have to be able to do. So I have this right here, and it says, all right, the rate of change of the volume, which is what? dV dt, the rate of change of the volume is increasing at a rate of 4 cubic meters per hour. So 4, and you can write meters cubed per hour if you want, but I'm just writing down info right now. If the height of the cylinder is fixed at 2, okay, height's not changing, then I can plug that in, right? So I don't need a variable for that. That's 2. It's fixed, which means there is no rate of change of height, right? So if the height's 2 and the volume's changing, what must be happening? Cylinder's just getting fatter, isn't it? It's got to remain a cylinder. It can't get taller. It's stuck at 2, so it's just getting bigger this way, right? Through the miracle of illusion. Whatever. All right. So if the height of it is fixed, determine the rate at which the radius is changing. So what is that? So I'm want dr dt when what? When, at the moment, when what? When the radius is 3. So I look back at this and I go, well, when I take a derivative of this, I'm going to rewrite it to look a little better. 2 pi r squared. I'm going to have a dV dt and a dr dt. Great. I've got the dV dt. I need the dr dt. I'm good. So right there, I can come in here and do what? Hold on. Oh, sorry. I'm looking at the wrong problem. Okay, right. So right here, I'm going to get dV dt equals 4 pi r dr dt. Again, don't forget the dV dt's and dr dt's or your problem's butchered. Especially this one. You forget the dr dt, you're like, wow, where'd it go? I can't even answer the question. And at this point, I'm just plugging and chugging, right? 4 in there, 4 pi radius 3 dr dt. And how do you get rid of a 12 pi? Divide by a 12 pi. And you can see the 4 and the 3 and the pi all cancel. and I get 1 over 3 pi. Now, what are the units on a dr dt? What would a radius be measured in? According to this, a meter. And then time would be measured in what? Did I say? Yeah, hours. So meters per hour. And again, those units are important on these. If it doesn't mention units, you don't have to worry about it. All right, now, I'm changing up the problem for part B. All right, so here's part B. Assume the volume is fixed. Okay, so here we go. Here's our cylinder. So assume the volume is fixed at 20. So now, if I go back to my equation, volume equals pi r squared height. If the volume is fixed, then I'm plugging a 20 in there. That is not changing. Right? Anything never changes in the process. You plug that number in. So, because if you don't, you're going to get a rate, and the rate's 0. It's going to make it go away anyway, whatever. So it says it fixed at 20. So I know the volume's 20. I'm plugging that in. It says the radius and the height are changing. Okay, so that means if the volume's fixed, I'm blowing this thing up, I guess it might get skinnier, right, and taller, or maybe it gets fatter and wider and less height, whatever. But it maintains 20 cubic meters. So determine the rate at which the height is changing. What is that asking for? dH dt, right? If it said determine the height, that's asking for h. But it says determine the rate at which the height is changing, dH dt. So that's what I want to know at the moment. What? The rate of change of the radius. So at the moment, dr dt is 2. And the radius is 2. So I want to know what is that rate of change of height when the dr dt is 2 and the radius is 2. Now this one's a little trickier, and you'll see why in a second. But first of all, I look at it and I go, okay, I got 2 variables, so I am going to have a dr dt and a dH dt, right? I have the dr dt, I need dH dt, I'm good. Problem you'll see in a second is this. Take the derivative, and what happens? The derivative on the left is a 0, and what happens on the right? It's a product rule. So whenever I have a product rule, I like to group the coefficient out front with whatever the first variable is. And just, instead of factoring it out and doing it, multiplying it back in, to me, it's easier this way. So here we go. First, d second is dH dt. Plus second, h. D first is 2 pi r dr dt. Now take a look at this. This is where this one's a little trickier. In this, when you go to start plugging in, check it out. I've got my pi, great. I've got my r squared, great. I know r is 2, plug it in there. I got my dH dt, perfect. I'm solving for that. I can leave that in there. Then I got my h, not perfect because I do not know it. I've got a 2, I've got a pi, I've got another 2 for r, and I got a dr dt, which is also 2. So everything's in there, but I don't know h, do I? And if I don't know h, what do?
I think you just like solve for h earlier.
I do. That's exactly what I'm going to do. So what I'm going to do, if I ever need to solve for a variable that I don't have, not a rate, but a variable, remember, this is the quantity equation, right? This is the rate equation. So if I ever need another quantity, go back to the quantity equation and go, well, looks like I'm looking for the height when the radius is 2. So I'm just going to find this, I'm going to go over there and say, oh, I'm going to just plug 2 in there and solve for h. So I'm going to divide both sides by a 4 pi. Cancels the pi, cancels the 4, and h is a very ugly 5 over pi. And I'm going to plug that in. But here's where I want to caution you again. Guys, don't solve for h and r and plug them in there too early. Never plug in an amount into your equation and differentiate that unless that amount never changes. And we are seeing that the only thing that's fixed here is volume. The rate and the height are changing. So don't plug constants in for them until after you differentiate. You can solve out to the side and find those other values, We did that with the ladder, didn't we? Remember I said the base of the ladder was 7 and we needed the height? So we went back and said, oh, 25, 7, 24 triangle. Oh, the height must be 24. We used that, but we didn't plug 7 to 24 in the equation early. We waited until after we took the derivative. Yeah.
How come you can solve for h using the 2, even if it's not like that equation is not at that moment?
It is. Well, this is an equation at any moment, right? This is an equation that relates any r and h that's out there. But if the r is 2, that would be the height that would go with it at a volume of 20.
Then why wouldn't you just put
Because it's changing. This is the height at that moment, right? I mean, think about it. When the radius is 2, there's got to be a height, right? There's not more than 1. If there's more than 1 height, then the volume would be 20. So there is some h that goes with that r. I just don't know it. So I can find that particular h, but there's also a zillion other h's that go with those zillion other r's. So because the r's and the h's are changing, they can't go in here before I differentiate. They said the volume was fixed, right? If the volume's fixed, then I don't need that v. It's not changing. And taking a derivative, you know, like literally, if I took the derivative of this, I'd get a dv dt, right? What's the rate of change of the volume? If it's not changing? 0, right? I mean, think about it. I can still, if I took the derivative with the v in there, I'd get dv dt equals blah, 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 blah. And you'd be like, man, I don't know dv dt. Yeah, you do. What is the rate of change of the volume if the volume's not changing? 0. So you could do that and leave those variables in there all the time, but I just prefer that if it's a constant, throw the constant in there. Then it's totally obvious when you ddx both sides, right? Or I'm sorry, ddt both sides. Then it's totally obvious, oh, when I take a derivative of a constant, I get a 0. But my r and h are changing on this, right? Think about it. If this was a 20-gallon, whatever that measure is, if that was a 20-gallon container, there's all kinds of 20-gallon containers, right? There's some that look like barrels, right? Hold maybe 20 gallons. Well, 20 gallons is not that much. But there's some that look like barrels that are about this high. I could push it down and make it a big, like, swimming pool looking thing, right? That held 20 gallons. There's all kinds of different radius and height combinations. We're talking about this particular one. And then at this point, you're just solving for this, right? So how do I solve for dh dt? Most people kind of want to clean this up a little bit. But look.
Teachers, at this time, please
40.
conduct your virtual tornado drill guidelines with your students. Again, at this time, please conduct your virtual tornado drill guidelines with your students. Thank you.
I mean, sometimes it's so bizarre what we do. I think we're going to look back in 10 years and go, were we that stupid? Like, I guess it makes, okay, if there's a tornado, what do you think we're going to do?
We're gonna go downstairs.
Stay by these windows, shards of glass in our face? No. We're going to go downstairs where?
Like the dungeon, like.
Yes, we're gonna head we're not gonna be under here, right, with more windows and stuff. We're gonna go down into that little horseshoe area and just follow the path. There should be. You just had to post them.
Can't everybody fit in this storm shelter? That's why they designed it like that.
There are enough time.
I mean, it's big, but it's not that big.
I think by protocol, like when they design it, it has.
Terrible map. It says evac route. Go to the stairs. And that's it.
Nice.
So you just stop on the stairs. But typically what they do is, you know, where the lunchroom is, the hallways on either side of the lunchroom. So everybody kind of goes to there and just lines up in those hallways and sits down. I think it's a pretty solid building. I mean, there's a lot of concrete. It's not built of like metal or whatever. I mean, it's all block wall, and we've got this massive hill. There have been tornadoes that have gone over the top of this building back in the late 80s, I think it was. One just went, and it just misses. We're pretty safe. I mean, granted, I don't want to be like face to the window here with high pressure and low pressure situations occurring. But anyway, are we good on this? All right, so talk to me about what you see right here. DHDT, what's height measured in? Height's measured in meters, and then time is measured in hours. So meters per hour. Now, talk to me about that. It's negative. What does that mean? So at this particular situation, the height must have been getting smaller. So right there, when the rate of the radius is getting bigger, the height is getting smaller. The rate of change of the height is negative. So the height is actually reducing its height, which makes sense, right? If I have to fix volume.
Jinx, you want to assume.
Do what?
So you want me to assume Jinx.
What did I do?
We said the same thing at the same time.
Oh,
It
gotcha.
makes sense.
We just did that.
We just did this. This was another trough problem, but just notice right here, base, height have a 2 to 3 ratio, right? So they're not the same. So this is a situation where you would want to go, okay, like before, I'm going to have a 1/2 base times height times length. My length's not changing. It's 5. So I can replace that. That gets me to 5/2 BH. But as you read through this problem, you're going to see some issues that you might have. So remember, one of the things is base over height has a ratio of 2/3. So you get 3B equals 2H. So that's your relationship, right? If I want to replace H and get it out of there, solve for H and replace it with the 3/2 B. If I want to get rid of B, solve for B and replace it with the 2/3 H. And you can get rid of one of those variables that way and make your life easy. But don't get tripped up by this. This is where people get tripped up all the time. I think I'm doing maybe a better job of kind of meeting it before you run into it. But sometimes you get really tricky problems. This is a 1987 problem. 87 is the year after I graduated high school. It was a long time ago. But this was a 9-point problem. You can't find a whole lot of these anymore. It's been at least 20 years, I think, since I've seen a 9-point problem. But notice what they did. They said, what's the rate of change in the height? I certainly want that in there. But it says, at the instant when the trough is 1/4 full by volume. 1/4 full. So how would you figure out what that means here? How do you figure out when the trough is 1/4 full? Wouldn't you need to know what the full volume is? Well, what is the full volume of this thing? You've got all the, right? 1/2 base width height. So 1/2 of 30. Are you following me? If the length is 5 and the base is 2 and the height's 3, that right there is 30. So half of that's 15. So a full trough would be 15. What's 1/4 full? 15/4. So this problem is made to be wordy. I try to avoid that on my tests, but it's just wordy for the sake of being wordy. So they're basically saying on part B, what is the rate of change in H? They're saying, what is DHDT when the volume is 15/4? Weird. That's what they're saying. So sometimes don't let the wordiness kind of get to you. Just think about it and don't be freaked out. So first thing said, find the volume of water in the trough when it is full. Well, that was what I just did, right? Volume is 15. You probably got a point for that, right? As long as you know the formula, 1/2 base width height. I'd probably write more than 15. I'd probably write 1/2, 2 times 5 times 3 is 15. And then I always use feet. Volume is feet cubed. And then the next problem is, what is the rate of change in H? What is DHDT? Right? So I'm looking for, what is DHDT? I've already written that. When the trough is 1/4 full. So right here, I need DHDT, right? It says water is being siphoned out of the trough at a rate of 2. So what is that giving me? dVdt is what? -2. Because if I'm taking it out, the trough's water is decreasing, right? That makes sense? So -2. So great. I'm great with an H. I'm great with a V, but I'm not great with a B. I don't have any information about how that's changing, do I? So what can I do? I'm going to solve for B in terms of that H. I'm going to replace B with 2/3 H. 5/2, 2/3 H. Bring down the other H. And now my volume is 5/3 H squared. Now I'm ready to go. Y'all seeing that? So again, I'm always looking at what am I given? I'm given these two rates. I'm not given any rate for B. I need to get rid of the B. Or do a completely separate related rates problem, which I don't really have any desire to do. So here's me taking the derivative. dv dt equals 10/3 H, what? dH dt. And at this point, I'm plugging and I'm chugging. -2 in there. What's my height?
This concludes our virtual tornado drill. Thank you.
So
Oh, goodness. So what's my height?
I don't know.
The volume's 15 force. Now, if I need another, what did we do on the last one? If I need another amount, what do?
You just put it in.
I go back to the amount equation. Now, I really don't want to plug it into this amount equation because there's all kinds of variables. Why don't I plug it into that amount equation and find the height? So what is the height when the volume's 15 force? Right? So again, this thing to me is messy for the sake of being messy, but it's not doable. And you got to remember, back in the 80s, not everybody had calculators, and very few, if any, had graphing calculators. Anyway, this is what I'm doing. I'm going 15 force right there, and I'm solving for H. And when I get that H, I plug it back in there. Hey guys, keep plugging away at these. Do the best you can, and come to me with questions if you have them. We're still going to do these for a few more days, so plenty of time to let it click.